Today we're going to look at the history of the periodic table. Your objectives for today are that by the end of the class you'll be able to tell me the differences between Mendeleev's original periodic table, how it was organized, and how we currently organize our periodic table, and that you'll be able to explain to me how periodicity, or things repeating in a period, works for the periodic table. Okay? So, prior to 1860, scientists had all this new information about elements, but it was all kind of wishy-washy. Some people had some information and some people said it was different than that, specifically when we talk about atomic mass. Up until this point, they hadn't come up with a consistent way of doing it. So some people would calculate it one way, some people would calculate it another, and they would wind up with different answers and then use those answers in compounds, and things just kind of snowballed from there. So the chemists got together and they said, nope, can't have that. We need a standardized way to do this. So they had a conference to try and answer that question, to try and come up with or propose a reliable way to calculate atomic mass every time. And they did. They found it. There was a guy at the conference, and he proposed his idea, and it was a good idea, and it worked, and people liked it, and so they stuck with it as their reliable way to measure atomic mass. So now that they have atomic mass, and they know it for sure, now they are interested in finding out, how does atomic mass compare to the chemical properties and the physical properties of these elements that we have. Several scientists then took that information and they started doing some research, and they contributed to what we have now as our modern periodic table. We're going to talk about a few of them. The first, and perhaps the most important, at least in my opinion, is Dmitri Mendeleev. I would consider him the most important because he was the one who designed the very first one. You often hear him referred to as the father of the periodic table because he was the first person to make a periodic table, to organize the elements in this way that we're going to discuss today. So what he did was he took a note card and he wrote down each element along with its atomic mass that we now had a way to calculate, and its known physical and chemical properties. So this is very similar to what you guys did yesterday, okay? Except he had never seen a periodic table because one did not exist, and he had far less information than you had on your cards because, remember, we're still learning about elements at this point. So we don't have all the fancy information about ionization energy and atomic radius and things like that, okay? He had what he was able to observe with the tools of his time. But he went ahead and forged ahead anyway, and for that we are grateful, okay? And what he did was he started arranging them by their similar properties. So, if they were physically similar, or if they reacted chemically similarly in the same situations, he would try to put them in groups. And he started noticing a connection between their atomic mass. And so he started arranging these by atomic mass, and then noticed that as he arranged by atomic mass, certain chemical properties appeared at regular intervals. Okay? So by regular intervals, we mean every specific number of elements, there would be another element that had these same chemical properties. Okay? So, but this was a regular number. It wasn't like after 2 elements, then it showed up again, and then the next time after 7 elements it showed up, and then the next time after 5 elements it showed up. No, it was a regular number. It was a pattern that appeared in his data. Okay? And this is where we get the name for our table, because when patterns appear at regular intervals like that, we call them periodic patterns. And so Mendeleev called his table a periodic arrangement of the elements. And so we have the basis for our modern periodic table of elements. There is a picture in your book of Mendeleev's table if you'd like to look at it. It's a far cry from what we have now, but it's very cool. So, there were a couple of exceptions to Mendeleev's table. A couple of times where if he was going by atomic mass, the next element that should have shown up didn't fit in his grouping. And so he would put them into groups with similar properties even though the masses didn't line up. Now we understand that the reason that was happening was because those atoms had certain isotopes that were very heavy, and they pulled their atomic mass towards the heavier side, and so they didn't fit in the periodic table where they should have because of their mass, because they were being affected by an isotope. But even with all of those exceptions, which there were not a ton, there were just a few, even with the exceptions and the flaws of Mendeleev's periodic table, it was still a very good periodic table. In fact, Mendeleev was so confident in his table that he pointed out several gaps in the table and predicted that we would discover elements that fit into those gaps, and then predicted the properties of the elements that would show up in those spaces. And within several years, they not only discovered elements that fit in those gaps, but they were remarkably similar chemically and physically to the properties that Mendeleev predicted. So his periodic table, even with its slight flaws, was a very good way to organize the elements, and it stuck around. And people continued to want to improve on it, and they continued to research this connection between atomic mass and the periodic properties. The next person to make a breakthrough was Henry Moseley. He was studying some elements, and he discovered that the elements fit better into the patterns of the periodic table if you organize them by increasing nuclear charge, by the charge of the nucleus. And we know that since the nucleus, the only charged particle in the nucleus is the proton, what he was actually doing was arranging them by number of protons, which we now know as atomic number. Moseley's work set the basis for the modern definition of atomic number and set the precedent that we should use it to organize the periodic table. This is where we begin to understand the modern version of periodic law. Periodic law can be defined as the fact that the physical and chemical properties of the elements are a periodic function of their atomic numbers. A simpler way to say that, when we organize atoms by their atomic numbers, their properties show up periodically and regularly. Next up, John William Strutt and William Ramsay make their contribution. What happens is that in 1894, these two chemists discovered the gas argon. And argon had been around for a long time and in our atmosphere, but the problem is that it's just so unreactive that discovering it was difficult, because you're not going to find it in compounds and you're not going to see it react with something because it just doesn't react with things. So discovering it was a challenge. After they discovered it, they wanted to add it to the periodic table, but in order to do this, they needed to create a new group. What they did was they took helium, which was another recently discovered element, and they took argon, and they suggested that we make a new group of elements. Anybody have a guess what group they were adding? The noble gases. Yeah, so this was the inception of the noble gases as a group on the periodic table. Later on in 1968, through their work studying the other noble gases, Ramsay discovered krypton and xenon, and then way later on in the 1900s, the last noble gas, radon, was discovered. So we had this new group, and the only thing really separating us from our most modern version of the periodic table is the lanthanides and actinides. The lanthanides and actinides are tricky because they're radioactive, and some of them aren't found in nature and can only be synthesized in the lab. So it took into the 1900s before they were all discovered and totally understood and put into groups on the periodic table. But at that point, we had all of our elements and we had our modern periodic table set up roughly the way we have it now. The periodic table, we said, shows elements properties and how they line up periodically, and we're going to kind of discuss what that looks like. Okay, so we're going to use the noble gases as our example, but then I'm going to show you how this fits with all other groups on the periodic table. Okay, if we start with the first of the noble gases, helium, and we start going through the atoms through the elements in atomic order, the atoms and elements that come next are completely different chemically and physically from helium until we get to neon, which just so happens to be the next noble gas. And the same process repeats it as we go from neon through the elements until we get to the next noble gas after neon. Okay? They're very chemically different from everything else around them. And this happens in a regular, predictable pattern. Okay? That pattern is the difference between atomic numbers. The difference between the atomic numbers is 8, 8, then 18, 18, and then 32. And this appears over and over in different groups on the periodic table. And we're going to discover in the next lesson that the reason for that is because of the arrangement of the electrons around the nucleus. Okay, let's take a look at this on an actual periodic table. Oh, I'm going to have to shrink this, aren't I? Okay. Technology issues aside, let's look at this periodic table here, okay? Helium has an atomic number of 2. If we go up to neon, the difference between those is 8. Between neon and argon, the difference is 8. Between argon and krypton, 18. Between krypton and xenon, 18. And then between xenon and radon, 32. The same pattern appears over here. Between 3 and 11, we have 8. Between 11 and 9, 8. Between 19 and 37, 18. Between 37 and 55, 18. Between 55 and 87, 32. This pattern shows up all across the periodic table. So that's what we mean by periodicity. Okay? These properties repeat at regular intervals, so regular that we can arrange them into columns where all of the atoms in a column have the same chemical and physical properties, or very close. Okay? I think it's really neat how it works out this way, that it's such a regular pattern that we're seeing happen that we can actually visualize it like this. And we're going to discover as we dig further into this that it's because of the arrangement of those electrons, and the arrangement of the electrons determines how those electrons are able to interact with other electrons, which determines how reactive something is. So we're going to see that those arrangements of those electrons is very important to why these happen periodically. All right, that is the end of our notes for today.